Yeah, so configure things, just to give you a little bit of background on us so you can understand why we're talking about this. We were formed out of, spun out really of Hewlett-Packard Labs on the basis of some work that was being done around large-scale distributed systems and how you keep them secure and resilient. And this was when we were doing our own kind of cloud engineering and into a number of areas. And particularly the focus was on resilience, and resilience is really all about managing change. So we have to assume that these systems don't stay permanently connected. They need to be able to recover from transient issues within the network, but also to be able to recover from changes in trust relationships, because a big failing in a lot of these things is they're designed and security is done as a single step during the design process, rather than recognizing when you've got systems that are maybe owned by different parts of the organization or even different organizations like we're seeing in kind of connected places, that those trust relationships should be something that you model and manage to be transient so that you can change them at any time. In some cases because you only want the trust relationship for a particular point in time, but quite often because you need to go back and revisit what you're trusted in the face of some kind of compromise. So on the basis of trying to exploit that work, we were part of the NCSC Cyber Accelerator program. And the work I'm going to be talking about today is primarily stuff we've been doing with them in this space of cross-domain. And everything I'm going to be talking about is published information from MCSC. But if you're involved in CNI or those kind of areas and you want to know more, there's a whole bunch of things that could be talked about in a slightly more controlled context. So what I want to get through today is I'm going to talk a little bit about what we mean by a cross-domain solution, and particularly the NCSC design patterns and where they came from, but particularly how that can be applied into IoT and into the IoT space, because it's not an area that's an obvious match, perhaps, for when you first start looking at the patterns and the information that's available. And then I'm going to explain how we've applied it in two particular cases. I'm going to talk about a LoRaWAN example, which is perhaps a more obvious IoT example of some work we were commissioned to do. And I'm also going to talk about how we apply the same thinking from these patterns at the edge, and talk about some work we've been doing with Cherry, which is the memory-safe architecture. I'm not going to go into lots of details about Cherry. There's a really good session about that back in here towards the end of the day. But I want to just take away with you how these patterns can actually be things that you can take and start to build into your thinking as you're starting to think about the architecture of these kind of systems. So with the first of those, cross-domain solutions, if you were to Google cross-domain security, what you tend to find is you'll find solutions from the typical defense players, so BEA, PA Consulting, those kind of guys. And you'll also find papers from NIS and NCSC. And that's because cross-domain really emerged from organizations that needed to deal with classification boundaries. You can imagine most of our organizations today are dealing with systems that at some part have to be internet-facing, or necessarily sometimes even the boundary between two different organizations, because trust is a very carefully measured and controlled things amongst these places. So the work was done really is really focused on how can I safely bring data in from a domain that I don't trust? And what does it mean to be able to safely bring data in? And likewise, what does it mean to safely be able to pass data back out to that system? So if you look at NCSC, they have a number of things that are published. This is their kind of the definition of what do they mean by cross-domain. It's really about systems that you trust differently. So these may, in the obvious case, be things that just belong to different people. I mean, a secure network and the internet is an obvious example of things where you've got different things that are trusted. But it can also be domains inside your organization that you manage perhaps from a single team, but you have a different set of trust policies around the way you want to operate things with. A key thing to take away from this is this isn't really about technology. I mean, I'm a technologist, and what I'm going to talk about will largely be technology. But really, this isn't thinking about the technology solution that you want to bring in on the back of this. It's really thinking about what are those trust relationships, and in particular, what should be the dynamic thinking around those kind of trust relationships. And it's clear that the more we're connecting systems together, actually the more trust relationships we're continually creating. And I think a lot of the time what we see in systems is those things get created kind of implicitly rather than explicitly. It's much easier to just draw the trust bubble a bit bigger when you're building a system to give you a domain to manage. What I'm hoping to give you from this is some thinking that can help you think about that solution slightly differently. You know, isolating is really easy, right? And we've for a long time built systems that need to be really secure by just making them air-gapped and not connecting them to anything. By and large, that's not really sustainable in today's world where things are drawing more and more on data and need data to feed them. So the whole idea of isolating stuff, where we've seen this particularly at the IT and the OT boundary, that's kind of getting in the way of what people now want to do with their businesses. But equally, you know, sharing is hard, right? Sharing is where you really start to get into problems. So you need tools, you need techniques, and you need the kind of patterns that the NCSC, I think, are publishing here to be able to help you understand what it means to be able to share those kind of systems. So if you look at what they define, so if you, and we've only got a short time here to go through, but if you go and look at what NCSC publish, there are a set of papers that are about the principles, and there are some design patterns for what you can do for import and export. And in those, they define a whole number of principles that you should consider, primarily looking at different types of attack that you're protecting against, so protocol attacks, content attacks, session-based attacks, so you need to not think of this as a shared import and an export path, because that's creating a kind of nasty loop for you to be able to bring things back out, keeping everything isolated. If I was to try to summarize them in terms of the thinking that we need for the next session, a key part is that you need to be able to inspect the data as it comes across the boundary. And playing back to one of the points that I think he's gone now, Toby was talking about, encryption isn't your friend here. If you need to be able to inspect the data because you need to check that the data is safe as you're bringing it in. Clearly, if you've got an encrypted payload, that's very hard to inspect. And in fact, when you start building an encrypted session between two things, you're tending to bring them into the same trust domain. So the data needs to be inspectable. You need to also recognize that in some cases, even the act of inspecting the data itself can be dangerous. There are attacks that can be built into a payload specifically to try to compromise the system that's at the edge that's trying to do the protection. So you need to, much as you would do in your, the mailroom used to X-ray parcels as they came in, and you do that in some kind of isolated state, you need to think about those kind of things and how you're going to build them in at the boundary. And that kind of, database attack is what can lead to a kind of persistent compromise. It might not be that the thing actually explodes the first time you look at it, excuse me, but it may well be setting the system up to fail some point later on. So you've got to also be really careful that there's no possibility to persistently compromise the systems. Thank you. So why this matters in the IoT space particularly? Well, we've got sensors that are out, and the sensors are typically out in some sort of untrusted location. So they form a key part of the attack surface. We're seeing a lot of CNI systems are starting to bring these things in, which is why particularly we were asked to look at this from the NCSC space. And these sort of systems exist in the IT and the OT space. And I'll move on because I'm apparently running a little low on the time there. The two examples to show you where this thinking applies. So here's a LoRaWAN example. I'm sure many of you are familiar with this in the IoT space. We're seeing these rolled out a lot. They're really attractive to people. They're cheap to deploy. They're fairly easy to deploy. They're a problem from a security perspective because they're cheap to deploy and they're fairly easy to deploy. You typically have sensors that are on some sort of radio network. You've got a gateway level that then translates that into the typical IP space. You have something that handles the protocols and something that handles the applications. And you might think here that the obvious boundary is at the point where you come in from the IoT to the radio space. Maybe that's the security domain, or maybe it's where it comes in from there into the LoRaWAN servers. But in fact, because one of the things that LoRaWAN does is it leaves its data encrypted end-to-end, which is a great feature from the system itself, the point where you've really got the cross-domain is actually has to be after you've done all that decryption. So you can think of the kind of LoRaWAN server that's providing that termination for the encrypted channels. That's something you still want to protect, but it's got to be the other side of your gateway. So it in itself is potentially exposed to persistent compromises. And it's the point when you come after that you want to think about, this is my boundary from a cross-domain perspective. That leads to a couple of interesting kind of problems in that the input path, we built a system to do this, and if anyone's interested, do contact us for more details. The NCSC pattern would say, well, what I need is a protocol break. Right? I need to be able to terminate the protocol. I need to get the data into some inspectable form. And ideally, if I can transform that data into some way, then I take out a risk of payloads that are in there in the way that I don't want them to be. Typically, they come through some sort of flow device. Data diodes, these are fairly standard, but a data diode on itself isn't enough. That's just protecting the flow control. It's one aspect of this import pipeline. And then having been able to actually inspect it, I can then bring it back into its original form or a different form and provide some kind of validation against that. And the validation might be based on the content itself. Does it pass schema checks, etc. You can also be doing analytics at this stage to check, is what that sensor's telling me really what I expected? Has its relationship with my network changed in any way? Because it's possible that the sensor itself has been compromised and systems are trying to feed in false information into me. So you have all of these things going on the import path. But as I said, the controllers themselves are now down in the persistent space. So what our platform allows you to do, because it was built to manage these kind of things, is to actually pass the configuration data out from the high side as well. And not just pass configuration down, and we do it as what's called a declarative model, so we're not relying on sessions here, we're not relying on kind of REST APIs. We're passing down approved definitions of the configuration that should exist, and we do it in a way that they can be authorized to go out, so we can be absolutely sure that the only thing we're sending out is actually the data that we want to. Because bear in mind, this is our kind of protected space. So you need to end up with patterns that potentially do have both an import and an output side, but that you've got to recognize that they need to be separate, and that you're not building session-based protocols across these things, because that would be a breach of where the guidelines need to be. And in particular, once you go to these patterns, this is what gives you the protection against this sort of persistent compromise. Although I'm relying on the state of this server here, because I can completely reconfigure it from first principles, in the worst case, this is considered purely ephemeral in our solution. If I needed to rebuild this in the center of compromise, I can do that from a known set of configurations that it should be in. And a key part about all of these systems is about that resilience. How do you recover when something becomes not trusted? And really the last thing you want is to have loads of sort of undo operations to try to think, well, what steps did I go through to get to this? Temporal sequence-based configuration is not great when you're trying to recover a system. And our platform and this whole approach was based around the assumption that we need to be able to bring things back simply by recreating what the trust relationship should now be, rather than having to worry about what it was historically. So this is a fairly straightforward example of doing the principles in the LoRaWAN space. The other space that I want to talk about as an example we used of looking at these patterns at the edge. So consider here a device that we're going to push configuration updates to. And this might be smart meter, home charge. As we've heard before, right? Lots of things are becoming connected that didn't used to be connected. And we're starting to rely on them to make decisions rather than just for monitoring. So if you think about the way the energy grid is spreading out to try to include home chargers and home batteries, all of those things are part of the attack surface. So we were looking at the example of, well, what does it take? What if a malformed configuration update could attack something? And if that feels slightly abstract, if you keep in mind that the CrowdStrike incident this year was effectively caused by this sort of a problem. There was a flaw in the system that reacted badly when a new update came into it that exposed it. And because of the trust relationship that was sort of implicitly there, or maybe you could say there of necessity from some other artifact of architecture, because of the trust relationship between the CrowdStrike agent and the window kernel, the impact of that was a lot wider than it really should have been. So the kind of protections that you really wanted to have in here is, well, we need to be able to validate the data before we make it available to the things that are going to try and act on it. But we need to make sure that validation is contained. We don't want the validation when we start to look at this data to make things explode. And parsers in software tend to be things that are fairly vulnerable to having unexpected data paths through them that lead to all sorts of problems. Right? And we want to make sure that when we do bring configuration in, if you look at the smart meters today are actually fairly complicated devices. You want to make sure that the data you're sending in, which might need to come from 2 or 3 different organizations, is only being made available to the right part of the system. So we built a system on the back of Cherry. So I'm not going to talk much about Cherry. There's a really good track. There's a whole track dedicated to this at the end of the day. Do come in and listen to it. We're part of that program through this Secure by Design initiative. We did some work taking these principles and applying them to Chariot, which is the real-time operating system that runs on top of this memory-safe hardware. So memory-safe hardware where the things that you might think of in software as protecting access to memory ranges are implemented down in terms of the processor itself. In particular, what that has as a model, as a runtime, it has three things that are really important to us. It has a compartment model that gives you a really strong set of guarantees around what your software is able to do or not able to do. So you can be sure that when your software runs, it's not able to affect areas of memory that it's got no reason to be looking at. In particular, also that it's got no temporal impact. Once it's run and it's finished, I can be sure it isn't able to have captured any of the data I passed it. It's not able to have written to any part of the heap or the stack that it's not able to talk to. And it also has, based off that kind of a way of protecting and being able to audit from compile time who's allowed to talk to who, which compartments are allowed to share which data with each other. So off the back of that, we created a resilient configuration broker, and we've actually so Chariot is an open source runtime. It came from Microsoft. There is a demos repository alongside it. We've contributed this back up there as an example of how to use both the NCSC patterns and the capabilities in Chariot. And what this really did is it took our configuration management platform. We used MQTT because that's a fairly nice way and proven way that we could talk. We implemented a number of aspects inside the Chariot here. We had a configuration broker, which is the thing that's really has the authorization as to who's allowed to see what. Particularly, we built a set of parsers for the data, and each parser is isolated. So the parser, when it runs in what Chariot calls a compartment. That means that it's got no heap quota. It's not allowed to allocate any memory. And one of the things I can do in Chariot that's quite nice is I can actually say, by the way, this pointer I'm giving you, you can only read it. You're not allowed to store it anyway. You're not allowed to do anything with it to have any kind of persistent impact to this. And what this meant was that we can show that the kind of attack, like we saw in CloudStrike, of something that breaks the parser, sure, it's not going to be parsable, right? If you pass bad data in that the parser can't cope with, it can't parse it. But the really important thing is we can be sure from the software guarantees in this case that that's got no persistent impact onto the system. The bad values never get through to the controllers that should be seeing it, and neither do they have any effect on the next value that's going to come in to try to parse it. And this is an example of that cross-domain thinking of, I need to be able to look at data as it comes into my system, I need to be able to validate the content of it, and I need to remember that even the act of trying to do that itself can be part of the threat profile, is where I think you can take these patterns that NCSC have produced, that remember came in a battle-hardened from what they're doing really at the edge of government and military systems, and take the same kind of thinking and start to apply it into these sort of domains and draw on the kind of capabilities that we're now seeing beginning to become available through some of this work like the memory safe runtimes. So, key takeaways. So the cross-domain principles and the papers that are there from NCSC, they're written and they're used for classification boundaries. There is hardware that is necessarily expensive that operates in that kind of domain because of the kind of threats that they're trying to protect against. But the principles that are in there, and even the techniques and to some extent the software, and as I say, we have plenty of this in our platform. We're around all day, my colleagues here as well. Do come and talk to us about it. You can apply that into a lot of other cases as well. And the organizations behind these are quite keen to start to see that kind of thinking now permeate out. This really isn't just about the technology. Really, when you're thinking about these things, think about trust relationships you're creating. And in particular, think about what's the temporal nature of those trust relationships. What does it mean for my system to build it in a way that I can change my trust relationship? Whether I've got to change it because I've been compromised. You might have a compromised admin. That's probably one of the most common attacks you're seeing coming in. What does it mean to be able to just disregard their inputs into the system but still leave everything else in place? Trust relationships are key because we're creating more and more of them. Don't fall into the trap of creating them implicitly. Right? Every time you're thinking of connecting things together, think about what is the trust relationship you're creating and how do you want to manage it. And again, I said, isolation is easy, and isolation is great where you can afford to do it. I'm not advocating connecting things that don't need to be connected. But I think what we're seeing more and more is that's a shrinking space. And what we have to do is work out how to do the hard bit, how to do the sharing. And there are patterns that are there, and sometimes from non-obvious domains that you can bring in that you can use to help you do that kind of thing. So that's me. As I say, we're around all day. Do reach out to us if you're interested in any of this work or any of the platform that we have on here. Hopefully I'm kind of about on time.
A bit over.
Okay. I'll live with a bit over. Any questions, or otherwise I can pick them up afterwards as people do.
Can you wait for the mic? So it's just for the recording.
Yeah. Yeah, you've discussed Chariot, Maurice Wilks, the reincarnation, I guess, of Maurice Wilks's capability machine that I think I saw in the early 70s. But can you compare the effectiveness of this kind of capability hardware-based solution to language-based security ideas like Rust?
So I believe they're complementary. What I would say is we've applied stuff on top of Chariot. The guys that are running their session this afternoon, I know you've got the people that are coming in for that, are much better placed to look at that. What you see on the Chariot website, if you go there, is there's a really good set of kind of blogs being posted. There was one that David Chisnell, who's one of the architects between Chariot, posted recently that talks explicitly about where Rust and the capability type protections are actually complementary and can be used together. I mean, Rust is great, but there's an awful lot of C code out there that needs to be protected as well. So I think they're complementary. I believe what was there in the blog, but I'm probably not the best person to take that question into more detail.
Thank you. You're in the other jump.
Thank you very much, Bill.